All right, well, welcome back. We are on 4.4a today. And that means we are finally here, guys. We are finally going to look at the fundamental theorem of calculus. So big day for us today. Here's one homework question I got last time. So remember I said take a look at number or examples 4 and 5 on page 300. If you didn't do that or you're still confused, I did work out number 67. So if you want to see number 67 from page 307, go ahead and pause the screen, answer each other's questions, and then we will go ahead and move on to section 4.4a. All right, so today's a big day. We are finally going to get to the fundamental theorem of calculus. So I've been insisting that somehow integrals and derivatives are related. And so today I kind of want to intuitively talk about why that is so. All right, we will get to the fundamental theorem today. All right, so I want to do a few examples and hopefully kind of convince you of the connection between derivatives and integrals. So let's let f of x equal 5. All right, so y equals 5. And what does that graph look like? Okay, it is a horizontal, this is our Cartesian plane. It's a horizontal line going through the y-axis at 5. Right? Okay. So f of x equals 5, or y equals 5. The first thing I'd like for you to do is find the area under the curve between x equals 1 and x equals 3. So let's see if I can get a different color here. So from x equals 1 to x equals 3. See if you could find that area for me. So what are we getting? Hopefully we are getting 10, right? And that's a rectangle with base 2 and height 5. So this is, the base is 3 minus 1, which is 2. The height is 5. And 2 times 5 is 10. So the area under the curve is 10, right? And that's what this symbol means here. This elongated s, the integral from 1 to 3 of f of x dx, where f of x was 5, will be 10. All right, step 2, I'd now like for you to find capital F of x, some antiderivative of little f of x. So it can be any antiderivative you'd like, but find a function, think of a function whose derivative is 5. What are we getting here? Oh, now the red decides to work. One such function would be 5x, right? What's another function? 5x plus 1, 5x minus 1, 5x plus pi, 5x plus any constant. All right, but the simplest one would just be 5x. Okay, my last step for you, step 3, I would like for you to find f of 3 minus f of 1. So do that on your own while I do it on the screen here. So f of 3 will be 5 times 3. F of 1 will be, capital F of 1, by the way, will be 5 times 1. So I have 15 minus 5, which is 10. Where do we see that number before? Here, right? Okay, so hopefully you're catching on to what just happened. If I want to find the area under the curve, it happened to be the same thing as finding an antiderivative and then evaluating it at my two endpoints, right? Okay, let's try another one, see if it works. Okay, let's let f of x be 2x this time. All right, so if f of x is 2x, what does that graph look like, first of all? Okay. It is a line with y-intercept 0 and slope 2, right? So 1, 2, up 2 over 1. It looks something like that. Fairly steep, yeah. All right, now the first thing I'd like for you to do is find the area under the curve between x equals 0 and x equals 4. And how we would write that in calculus is this, right? The integral from 0 to 4 of f of x dx. Remember, f of x is this function, 2x. All right, so go ahead and see if you can find the area under the curve. All right, hopefully you got 16, all right? This is gonna be a triangle. Right, so this guy's gonna keep extending, and then we have some kind of triangle there. Let's see if I can do a better job. So I'm gonna have this triangle, this portion here. The area of a triangle is 1/2 base times height. So I have 1/2. My base is gonna be 4. And how could you find your height? It's going to be the y value when x is 4 up here, right? So that's actually going to be, what, 8, right? All right, so I have 1/2 times 4 times 8, or 1/2 times 32, which is 16. All right, now let's do step 2, just like we did last time. Find capital F of x now. What is some antiderivative for 2x? Well, one such antiderivative would be x squared, right? That's not the only one. X squared plus 5 would work. X squared plus 34 would work. Any one, any antiderivative is fine. All right, let's try this weird one. Let's try x squared plus 34. This is an antiderivative for 2x, right? If I differentiate this, I get 2x. All right, so step 3, let's find f of 4 minus f of 0. Well, f of 4 is going to be 4 squared is 16 plus 34. So that's f of 4 minus f of 0. Well, 0 squared is 0. Plus 34 is 34. And what happens to the 34s when I combine like terms here? They vanish, and I'm left with just 16, which is exactly what you got when you found the area under the curve. All right, so this is the idea between the first part of the fundamental theorem of calculus. Let's take some time and draw this picture in your notes, please. Okay, so I have some arbitrary function y equals f of x. And let's say I want to find the area under the curve from x equals a to x equals b. Okay, so far, our only methods for doing this was if we had somehow had a really nice shape, right? Like the rectangle we saw first, or the triangle we saw second. Our other tool was to use a calculator, right? Now we actually have a tool to find area under the curve by hand. Okay, so if I want to find this shaded area here, which remember is written like this in calculus, the integral from a to b, these are x values on the x-axis, right, of f of x dx, then this is equal to capital F. And which one do I evaluate first, the left hand or the right hand? We evaluate at b first, so the right, minus f of a, capital F. Okay, where capital F is an antiderivative for little f, right? So we write it like this, where capital F prime of x is equal to little f of x. Do you agree with that? If I differentiate the antiderivative, I get back to the original, right? So capital F is an antiderivative. Any antiderivative, right? Of little f. Okay, so make sure you have all of that in your notes. Okay, in words, I have it written here. I think the picture is just as good, but if you want to see it in words, the fundamental theorem of calculus, part 1, says if f is continuous on a closed interval ab, and capital F is an antiderivative of little f, then the integral from a to b, in other words, the area under the curve, of f of x dx is equal to capital F of b minus capital F of a. And once again, remember that this capital F is an antiderivative of little f. All right, I'm not going to prove this for you today. So you kind of know the depth of what you're studying at this point. When I took advanced calc 1 and 2 in grad school, I took one of my comprehensives over them, and these were my flashcards, 150 flashcards with theorems and their proofs on the front and back, and somewhere in there is the fundamental theorem of calculus. So that was one of the many proofs we were tested over. All right, so let's go ahead and try a few examples here. All right, so I have the integral from x equals 1 to x equals 2 of the quantity x squared minus 3. Okay, so remember, this means find the area under the curve of x squared minus 3. And this guy here its graph takes what shape? Takes the shape of a parabola, a concave up parabola, right, opening up. And it's a standard parabola shifted down 3 units, right? So it looks something like this: 1, 2, 3, right? Okay, so the fundamental theorem of calculus says if I want to find the area under the curve, I can actually just find an antiderivative and then evaluate it at 2 and at 1, subtract them, and that's my answer. All right, we'll go ahead and check on our graphing calculator afterwards too. Okay, so an antiderivative for x squared would be x cubed divided by 3. And an antiderivative for 3 would be 3x, right? And we'll evaluate this expression at 2 and at 1. So if I plug in 2, 2 cubed is 8, so I have 8 thirds minus 3 times 2 is 6. Okay, so that's f of b, or f of 2 in our case. Then minus, and let's go ahead and open up brackets. So I subtract the whole expression here. Now we're going to plug in the lower limit, which is 1. So if I plug in 1, I get 1/3 minus 3, right? Okay, no calculators yet. Please do all this by hand. So I like to combine my fractions with common denominators first. So 8/3 minus 1/3 would be 7/3. And then I have -6, and this is going to be a +3 when you distribute this negative, right? So that will be -3. All right, now let's go ahead and get a common denominator. This 3 can be written as 9/3, right? So I have 7/3 minus 9/3, which is going to be -2/3. That's my final answer. Now, why am I getting a negative result? If I go from x equals 1 to x equals 2, I'm actually going to have more area below the x-axis than I am above it, right? So I'm going to have more negative area than I do above. Okay, by the way, what's the calculator going to spit out as a decimal? Negative 0.66667, right? Okay, let's try this on our graphing calculators. We're going to do it on both the home screen and the and your graphing screen. All right, so let's first go ahead and do it graphically. So you have your function was x² minus 3. And let's go ahead and graph that. There's our standard parabola shifted down 2 units, right? Should cross the x-axis at plus or minus square root of 3, right? So right between -1 and -2 and +1 and +2. Okay, so now if you go second calc, we want to calculate the area, which is which number? Number 7. Our lower limit was 1. I would just type in 1, enter. And our upper limit was 2. I would just type in 2, enter. And it shades it there. You see you have a teeny bit of positive area right here. This is the same area we got. Yeah. It's the approximation at least. All right, go to your home screen. Now let's, if you prefer to just type it straight into your home screen, that's fine too. A couple ways to get to it. I just like using Math 9. So the integral from 1 to 2, and those are what kinds of values? Remember, those are x values. So from x equals 1 to x equals 2 of x² minus 3. State your variable here, dx. There's that. We may be able to turn it into a fraction. Let's see, there it is. All right, so there's our -2/3. So either way to check on your calculator is fine, but I do want you doing these by hand. Okay, let's try another. So this time I want to find the area under the curve of secant squared x from x equals 0 to x equals pi/4. All right, fundamental theorem of calculus says, at first we find an antiderivative, right? So first we do what we would do even if we didn't have these limits of integration. So what's an antiderivative for secant squared x? In other words, what function has the derivative secant squared x? Well, one such function is tangent of x, right? Or tangent of x plus c, but any antiderivative works. All right, so step 1, find an antiderivative of secant squared x. Then step 2, plug in pi over 4 and 0. By the way, you can write your notation like this with brackets around your whole expression. It's also acceptable to just write kind of like an absolute value bar, just one of them here. Both of these mean the same thing. They mean evaluate this expression at B and A and subtract. Right? I kind of prefer this notation, but either one is fine. All right, so now I'm just going to plug in pi over 4 and pi over 0 and subtract. So I'm going to have tangent of pi over 4 minus tangent of 0. Okay, yes, you have to remember your unit circle now. All right, pi over 4 is in the first quadrant in between the x and the y, right? So this ordered pair here is square root of 2 over 2, comma, square root of 2 over 2. And tangent is sine over cosine, or y over x. So tangent of pi over 4 will be this over this, which is just 1, right? Okay, now tangent of 0. 0 is right here. The ordered pair is 1, comma, 0. So if I do 0 over 1, in other words, y over x, that is 0. And my answer is 1. Yeah. All right, let's check on our calculators. Just remember how to type these in. So first of all, we want the integral from x equals 0 to x equals pi over 4. All right, and then I want to find the area under the curve of secant squared x. So I'm going to go ahead and open up another set of parentheses. Now, secant is the reciprocal of what? It's the reciprocal of cosine. So to get secant, we're going to do 1 over cosine. Okay. I'm going to close that set of parentheses that I created, and then I want to square that. All right, so that's how to type in secant squared x. And there's our answer, yeah? Same answer we got, 1. All right, I have one last example for you. This is a motion example. I believe you have one kind of like this in your homework. It says a particle travels on the x-axis with velocity given by v of t equals 2t. If the particle is at x equals 1 when time t equals 0, then what is its position when time is equal to 2? All right, well, velocity is related to position right here. How? Well, velocity is the derivative of position, right? So would you agree? I want to find position, right? So would you agree that position is equal to the antiderivative of velocity? Yeah. So velocity in this case is 2t. So position must be equal to the antiderivative of 2t, right? What's the antiderivative of 2t? T squared. But then we can't forget our what? Our plus c. Okay, so this is the position function, kind of, right? I'm not real happy with that plus c. I'd like to know what that plus c is. But look here, you are given an initial condition. It says when time is equal to 0, so when t is equal to 0, your position is 1. So let's plug in that ordered pair. So when t is 0, my position is 1. So that means my constant must be equal to 1. All right, that's good news for us. Now I can go ahead and come back to my position function right here and plug in that c value. So my position function, x of t, is equal to t squared plus 1. All right, now let's see if we've answered the question. Now it asks us, what is its position when time t equals 2? Well, I have a function for the position. Okay, so this gives me the position at any time t. So how could I find the position when t equals 2? Well, I'll just plug in 2 for t, right? In other words, find x of 2. So x of 2 will be 2 squared plus 1, which is 4 plus 1, which is 5. And no units were given, so I'm just going to leave it at 5. All right. Well, that is section 4.4a. So you now have had an introduction to the fundamental theorem of calculus. Next time we will look at u substitution with definite integrals. So using u substitution to find area under the curve. All right, guys, see you next time.